Hello everyone. Today we're going to discuss about hybridization. If you just remember last week, we had a discussion on resonance structures and how to write resonance structures and compare their stability, major, minor contribution as well. So this series of discussion on important aspects of organic chemistry would help you in understanding core areas in organic chemistry. So with this, I'll pass to show you some concepts in hybridization. The hybridization, as you might know, is a mixing of atomic orbitals. So mixing of atomic orbitals happens in order to generate shapes and geometry that's optimized for an overlap. That means each atomic orbitals would combine with other atomic orbital to produce optimized atomic molecular orbitals. So if you have one s, for example, plus 3p orbitals, it would generate obviously sp3 hybrid orbitals that are 4 sp3 orbitals. So the number of combination of atomic orbitals produce the same number of molecular orbitals. That's also one thing you need to remember. When it comes to shape and geometry, this shape and geometry are optimized for efficient overlap to create a sigma bond. So any hybrid orbital always makes a sigma bond. So for example, if you have an sp3 hybridized orbital, it combines with one s hydrogen atomic orbital and forming a sigma bond. In hybridization, there are sometimes unhybridized p atomic orbitals, which always makes the pi bond. So pi bond is always made of unhybridized atomic orbital, the leftover p atomic orbital. The other concept we need to remember would be hybrid orbitals are energetically degenerate. When we say degenerate, they are equivalent energies. They are of the same energy. As a review, hybridization is a mixing of atomic orbitals. The mixing happens in order to generate optimized orbitals that are effectively making sigma bond. The unhybridized p atomic orbitals in most cases make a pi bond, and hybrid orbitals are energetically degenerate. So if you just look at some examples of real life atomic orbitals making hybrid orbitals, we can just look at sp3. As you see here, you have three p orbitals in a py direction, in pz direction, and px direction. So the combination of one of the s orbitals, or for example, in a carbon, the 2s orbital, would generate a hybrid orbital. But remember, we have 4 atomic orbitals together with the s, 1, 2, 3, 4. They generate 4 molecular orbitals as well. So these are the 4 molecular orbitals. So this is an sp3 of one of them. So the addition of this s mixing with p will generate this atomic orbital. This is just one atomic orbital of the 4 that would be generated. So it is a 1 plus 3 to generate 4 atomic orbitals. So this 4 atomic orbitals, for example, when it comes to carbon, are degenerate, meaning that of equal energy. They are equal energy. They are also equal energy. They are degenerate. So for tetrahedral, the angle for this is, for example, when it's atomic carbon, which is have 109.5 degrees. That is very convenient for a tetrahedral geometry. So when you see all this, the combination, mixing of atomic orbitals to generate molecular orbital, which are actually hybrid orbital, is better saying it hybrid orbitals, would generate an optimized angle for the overlap to make, for example, here this can make an sp3 sigma sp3s 1s overlap, that is a sigma bond with hydrogen. Another hydrogen can come here with 1s, with 1s, with 1s. So there are 4. So this is how actually methane is formed, by sp3s sigma bond overlap. So sp3 hybrid orbitals with s of hydrogen make s sigma bond. So that's hybridization, is making orbitals for optimized overlap and as well as optimized angular angle, bond angles. Okay, let's see also sp2. Similarly, sp2 is a mixing of 1s orbital with 2, it could be px, py, 2 of them, and there is one unhybridized orbital. Remember here, you have px, py hybridized to create sp2 hybridized orbital. So that means 1s plus 2 of the p orbitals generate 3 hybrid orbitals, 3 sp2 hybrid orbitals. As you see, there are 1, 2, 3. So if it is in a carbon, that's what you see. There are 3 sp2 hybridized orbitals. The bond angle is 120 degrees. So these are the 3 hybrid orbitals, but in an atom, these hybrid orbitals are oriented in a planar arrangement at 120 degrees. So remember here, it's not shown here, but one of them remains as unhybridized when it comes to carbon. Let's say that is a PZ, is not shown here. So this is an hybridized p orbital. This is what is responsible for making a pi bond. So this is unhybridized p orbital left. Out of px, py, pz is not shown here. In sp, definitely there are 2 unhybridized orbital making 2 pi orbitals. Here it is only the 1s and 1p generating 2 sp hybrid orbitals. So these are the 2 sp hybrid orbitals. One is this one is this one. So there are 2 unhybridized orbitals that are the, here we are showing the px as a hybrid with this, but the py and pz are remaining as unhybridized. Therefore, it has a potential to make 2 pi bonds. So mostly you see this kind of hybridization in acetylene, for example. If you just look at this compound, this is sp hybrid, this is sp hybrid. So the 2 pi orbitals are made from 2 unhybridized p orbitals. Okay? So with this, once we have seen this, I'll just show you details of the hybridization. This is a concept where the orbitals that are involved in making a bond are optimized. That means the energy level of those valence electrons, where they are in the valence shell, would have an appropriate orbital so that they make a perfect bonding between 2 atoms. Remember that when we say orbitals, each atom would have, for example, if we consider hydrogen, it is a 1s1. If we consider carbon, it is 1s2, 2s2, 2p2. So if you just look at here, the S is paired to P has 2 electrons. That means if you just expand this in the px orbital, there is 1. In the py direction, there is 1 orbital. So the unpaired number of electrons, if you just look at here on carbon, they can only take maybe 1s of this, 1 electron, to pair up each. So the maximum number of hydrogens that a carbon can take based on this orbital distribution, so this is the number of electrons in the orbital, is, for example, if you just bring one electron, 1 of the s, interacting with this, it makes 1, another 1, so it would make CH2, not CH4. The compound that we know as a stable organic compound is methane, which is CH4, not CH2. So how do we make CH4? Based on the electronic configuration of hydrogen and the electronic configuration of carbon as they are. So it is not possible to justify how CH4 is formed just by looking at the orbitals. So hybridization is a concept where you are justifying or you are mathematically expressing how the orbital overlap happens, and the bond actually is made and it is stable to form a tetrahedral methane compound. So hybridization that is the concept. It's not just the orbitals that are found in each atom that just without any hybridization they would make the bonding. So CH2 doesn't exist, CH4 exists. So how do we accommodate 4 electrons or 4 of the hydrogen's orbitals that can come here? Because the valence electrons on carbon are, let's say, on the p, these are paired already, so you cannot bring anything according to what we have. So if you have 2px1 and 2py1 for the 2p2 configuration, the maximum you can have is 2 hydrogens, but CH2 doesn't really exist. So this concept or this idea of having CH4 can be only justified by hybridized orbitals. What are hybrid orbitals? So let's review now. So when we say orbitals, these are the lobes that contain the electrons to make the bond. For example, if you have hydrogen gas, which is a linear molecule, a non-polar covalent bond between the two is made from 1 electron of 1s1 and another 1s1 they overlap and make the bond to make this covalent bond by sharing these two electrons. So they make a sigma bond because this is made from one s electron. S orbital is a circular one, a sphere type. This is a 1s orbital where one of the electrons exists, and another one is 1s for this. So there are two s orbitals. When they combine, they become a cylindrical shape with the nuclei like this. And this is original one of the hydrogens. So you have this. So the bond that is made from SS overlap, the orbital that's made from SS overlap is called sigma bond. A sigma bond. Sigma bond is a single bond. So now we are going into details of what this bonding looks like by way of hybridization. So this is a simple case where an S and S overlap. So they make this cylindrical shape molecule where this bonding, where the electron density is high here, is a sigma bond, denoted by this symbol as sigma bond. Sigma bond is very strong, and also it is the longest one. We'll consider that later on. So sigma bond is what exists between two hydrogens. It is made from the overlap of one s orbital and another s orbital. So that made a sigma bond. Next, we will see a tetrahedral shape that is making a methane compound out of 4 hydrogens and 1 carbon. That is made by hybridized orbitals, not by just the combination of the atomic orbitals. These are atomic orbitals. Atomic orbitals. Just as these are atomic orbitals as well. But in order to make organic compounds, there is a concept what we call hybridization, where the atomic orbitals make certain transition and make appropriate energy level orbitals that can also perfectly overlap so that they can make a bond. So in the next discussion, I will show you how a tetrahedral bond in methane is made from hybrid orbitals. So CH4 is made not from atomic orbitals, but it is made of hybrid orbitals. That's the concept of hybridization. So those are hybrid orbitals. How are hybrid orbitals made? That is in the next discussion, what hybrid orbitals are. We told you about hybrid orbitals. We'll now discuss how methane, which is CH4, how methane is made. First, let's see just the atomic orbitals by themselves. For example, carbon in a ground state, that means unexcited carbon, which is a 1s2, 2s2, 2p2 configuration, would have its orbitals arranged by energy diagram. For example, the lowest is 1s energy. If you remember in your general chemistry, there are 2 electrons in the 1s. In the next 2s, there are 2 electrons with the spins, they are up and down. And there are, in the 2p, there are 2 electrons. If you remember, 2p orbital is a px, a py, a pz. There are 3 of them, if you remember, px, py, pz. But s is just spherical in shape. But in the p orbital, if I just show you the shape, one is in the py direction, right? One is in the px direction, one is in the pz direction. These are the 3 orbitals that each one of them would contain 2 electrons, 2 electrons, 2 electrons, a maximum of 6. But in carbon we have 2. Therefore, I would just make 2 electrons in this spin. So now this is just a ground state configuration, just the atomic orbitals for carbon. So as I already told you, if you just bring 2 hydrogens from an s orbital, you can only make paired up, always bonding is pairing up. So this can only take 2 hydrogens. Therefore, this configuration cannot allow you to make CH4. So what do we have? Now, from this, what we are going to do would be to hybridize these orbitals. That means if you hybridize, that means if we make a hybrid of an s and a p, if you take one of the s and hybridize it with the 3 of the p orbitals, you would make sp3 hybrid orbitals. So what does it mean is you have s and p, which are energetically very close, so you cannot hybridize this with that, but hybrid is to say that you are just trying to mix them. So the hybrid orbitals look like, out of this, hybrid orbitals. So what I did is just to mix up all of this, so the electrons have now space to go everywhere in the p. So this one electron would jump to this. So what it looks like would be a hybrid orbital where one of the s and 3 of the p's are hybridized. You already know you have these electrons, and there is one electron that jumped to this, one electron. There is one electron which was already here and occupies this. Look at this now. Now, this is a hybrid of an s and 3 of the p. That's why it's called sp3 hybrid orbital. Energetically, they are all the same. They are equivalent, and also they contain a single electron in each orbital. So sp3-1, sp3-2, sp3, sp3. So now what we have done, to just review back again so that you will not forget, this is a ground state configuration. Let's say this is ground state configuration. The ground state configuration doesn't allow you to make CH4. It's because the only thing you can pair up is a maximum of 2 hydrogens with 1 electron coming from each one hydrogen. Therefore, you can only make CH2. But CH2 doesn't exist in nature. CH4 exists. Therefore, our mathematical approach why CH4 is formed is one of the s orbital is mixed with 3 of the p orbitals to make 4 sp3 orbitals, meaning s and 3 of them, sp3 orbitals with single electron distributed on all over the orbitals. Now, since you have one s1 in hydrogen, right? Hydrogen has 1 electron in its valence shell. Now, if you just bring 1 hydrogen here, you are pairing up. The sp3 is making a bond with one of the s to make a paired electron, and another hydrogen with one s making another pair. Another hydrogen, 1s1, making a pair here. Another hydrogen making a pair here. So now what we have is 4 sp3 orbitals that have bonded, because this is an s, that have bonded with sp3 to make a molecule CH4 through sp3 hybridization. Now we can justify how CH4 is formed. In nature, you have methane, not CH2. Therefore, the way the orbitals have made possible by expanding or by mixing these two orbitals, the s and the p, we made an equivalent. They are all equivalent now. Equivalent orbitals, and they are also called degenerate. Degenerate means of equal energy. Equal energy. So now, since they are all equal energies, they have equal probability for making or accepting 4 electrons from hydrogen of 1s orbital. So I will show you the shape, and also if you remember, how was this tetrahedral shape formed? It all depends on the hybridization and the angle that I showed you, about 109 degrees for sp3 orbitals, came from this calculation. So in the next discussion, I'll just show you what sp3 hybrid orbitals look like and what is the shape that made CH4 in a tetrahedral geometry. Now we have the sp3 hybrid orbitals that are equivalent. As I already indicated, the 4 sp3 hybrid orbitals, they contain 1 electron each in carbon. Carbon with sp3 hybridized orbital looks like this. 4 of them are identical in energy, and each one of them contain 1 electron. So there are 4 of them. They are made of 1 s and 3 of the p orbitals. That's why they are called sp3 hybrid orbitals. They are made of 1 s and 3 of the p orbitals in carbon to generate degenerate orbitals or equivalent orbital orbitals that contain 4 electrons. So how does they look like? If you remember, CH4, for example, looks like this. When I was discussing about tetrahedral shape, this was my discussion earlier. So the sp3 orbitals are actually the ones which are shown here, basically. So let me draw the sp3 hybrid orbitals. So they are made of 1s and 3 of the p, and their shape looks like this. The lobes are like this, one of the sp3, another sp3, another sp3, and another sp3. There are 4 of them. Each one of them have 1 electron, 1 electron, 1 electron, 1 electron. So this is basically what you see in sp3 hybrid orbitals. Remember that since they are made of s and p, the p has the shape that's like this. So the hybrid orbitals have actually a lobe, which I didn't show because I don't want to complicate. This is actually the sp3 orbital. This is how it looks like, but I didn't show this small lobe here in all of them. But that's how the sp3 hybrid orbital looks like. Now, if we were to make the compound, this is just a carbon with its hybrid orbitals. we can bring now the 1s of the hydrogen with 1 electron. So it is spherical in shape. The s orbital is spherical. So it can come like this with 1 electron paired up. This is hydrogen of 1s. If you just bring it to make the bond between these two, there is 1 electron there, and this is a 1s of the hydrogen. This is also hydrogen here, 1s, to make a pair, and here also 1s of the hydrogen to make this pair. This is actually what this molecule looks like when you saw it in hybrid orbitals. So this is 1H, this is 1H, this is 1H. So a methane is actually made from 4 sp3 orbitals that are overlapping or make bond with 1s of the hydrogen. So 4 of the sp3 hybrid orbitals, sp3 hybrid orbitals, 3 means 3 of the p, and 1 of the s, with a total of 4 electrons on them, overlapping with a sigma of 1s are actually what is making the bond, the 4 bonds. And as I already told you, in order to improve the repulsion between bond pair, the tetrahedral geometry is a preferable one for sp3 hybrid orbitals, so that they can look like the distance between them is 109 degrees. 109 degrees, the angle. The angle is 109. So that is how hybrid orbitals are making a CH4 molecule. So it's just more complicated than like what you see here in a tetrahedral stick form, like I showed you earlier. But it's made from hybrid orbitals, and now you know how the 4 orbitals, the sp3, came from hybridization of 1 of the s and 3 of the p orbitals in carbon. So carbon comes with these 4 sp3 hybridized orbitals. So these are all hybrid orbitals or hybridized orbitals. And now one important point I want to mention, the overlap of sp3 with a hydrogen with 1s always form sigma bond. So that is a sigma bond. It's not a double bond, it is a single bond. It's called sigma. A sigma bond. So the overlap of an sp3 with 1 hydrogen when it comes in to make a bond, that is a sigma bond. So remember, this is a sigma bond, this is a sigma bond, this is a sigma bond, this is a sigma bond. They are made from the overlap of 1 sp3 with 1s to make this bond. So this is the overlap of sp3 with 1s, that is a sigma bond. So a sigma bond is made either by, like in hydrogen molecule, an overlap of an s orbital with another s orbital make a sigma bond. Another sigma bond is an overlap of 1s with a hybridized sp3 is always a sigma bond, always. So don't make any mistake in assigning what kind of bond it is. If it is sp3 and if it is overlapping with an s orbital, for that matter with any other orbital, it can only form a sigma bond. Now we are also, together with hybridization, we are also learning what type of bonding it is. It is a sigma bond. It's called a sigma bond. Okay, in the next discussion, we will be looking at sp2 hybridized orbitals. The sp2 hybridized orbitals are made of, with one of the s orbitals of carbon and with another two of the p orbitals in p orbital in carbon. So there is sp3, which we just discussed from hybridization of one of the s with three of the p. There is another one which is called sp2. There is also another called sp. So these are the type of hybridizations. These are type of hybridizations that are possible. sp3, sp2, sp. So since we have just finished the discussion on sp3, I will pass on in the next section to sp2 hybridization. Discussion continues. Now I want to show you what sp2 hybridized carbon looks like in the orbital formation and how the bonding happens. So in ground state carbon, you have a 1s2, 2s2, 2p2 in electronic configuration. So these are just atomic orbitals. When you say it's hybridized, that means in excited states of this, we are trying to make sp2, meaning 1s and the 2p orbitals are mixed. That means you are creating, usually we don't consider the inner one, that's the most close to the nucleus, but we are just considering valence electrons. So we are mixing one of these orbitals with two of these p orbitals. That means we are just taking one to make three sp2 orbitals. These are sp2 orbitals of their lower energy, but one of the orbitals, because there are 4 atomic orbitals, 1, 2, 3, 4, but one of them is not hybridized. So it will be a little high in energy. So it remains, it could be the px, the py, or the pz. It doesn't matter which one, but one of the p orbitals is not mixed because we are just mixing one of the s and two of the p, which are degenerate orbitals. Remember, I have said all hybrid orbitals or hybridized orbitals have of the same energy. That's why we call them degenerate orbitals or equal energy. One of them is a p orbital with one electron, which is not hybridized, but the 4 electrons are distributed like this. So 1, 2, 3, 4 electrons. So this p orbital, one of the p orbital, is not hybridized. So this is not hybridized. That's why it's at higher energy than the 3 ones. These are hybrid orbitals. So this is how sp2 hybridization happens from a ground state of carbon, for example. It could be oxygen. You can do the same hybridization pattern, but here carbon undergoes sp2 hybridization like we have seen in sp3. So there are now 3 sp2s and 1 p orbital. So if we were to draw this in a drawing form, the sp2 orbital configuration would be sp2, one of the sp2s with 1 electron, another sp2 with 1 electron, this one, and another one sp2 with 1 electron on this. But remember that, as I said, this sp2 are now hybrid orbitals. These are the ones which will be, for example, making a bond. But remember, there is a p orbital still on carbon. That p orbital is perpendicular to the sp2 orbital. the sp2 orbitals are aligned with 120 degrees. Remember now, for sp3 we said it is 109. For sp2 configuration, since there are 3 lobes, they are in space at 120 degrees. Remember that. Now, if we consider all of the sp2s are on the plane of the board, there would be the p orbital perpendicular to the plane of the board. What it means is it's 90 degrees to the sp2. For example, if this is all of the sp2 orbitals with carbon at the center and a flat molecule, a flat configuration, then the unhybridized p orbital stands at 90 degrees to this. So I will be just drawing it so that you will identify it as a p orbital, but it is 90 degrees to the surface of this sp2 orbitals. So this is 90 degrees to the red color is unhybridized p orbital with 1 electron. So it's only 1 electron on a p orbital. So that's the p orbital. So in chemical bonding or in making a bond, what happens is, for example, to give you an example where we have a pi bond. So a bond that's made through a pp interaction is called a pi bond. But let me give you an example. Just keep this in mind. We have C, H, 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 H. This molecule is called ethylene. We'll discuss it later in detail in the future. It is ethene. It has a double bond, 1 sigma bond and 1 pi bond. I will explain which one is a pi bond. So suppose this carbon is an sp2 hybridized carbon. Actually it is sp2 hybridized carbon, exactly like this. If I make another one exactly like this, C, sp2 hybrid orbital, sp2 hybrid orbital, and still 1 p orbital remains unhybridized on this carbon as well, exactly like p. It's exactly 90 degrees to the surface. So this, all the sp2s are on the plane, and then the p orbital is 90 degrees to the plane of the sp2 hybridized orbitals. Therefore now, if you just look at this, this actually is made by the overlap of this sp2, sp2. So this sigma bond is the overlap of this. So they come, make the bond. This is a sigma bond. Sigma bond. This is the sigma bond right here. And the other one, we call this a pi bond. This bond is a pi bond. That is made by the ones which are sticking like this, the p orbitals, which are not unhybridized, but each one of them have 1 electron on them. They make a bond. So that is the pi bond from this carbon to that carbon. It's called a pi bond. A pi bond is made from unhybridized p orbital interacted with another p orbital, unhybridized. Okay? Now, after having all this, remember, hydrogen has an s orbital which can easily overlap with sp2 as a sigma. This is one s with one electron, that's hydrogen. This is one s of hydrogen with one electron, with one s of hydrogen with one s of hydrogen. This is basically how it looks like a hybrid orbital that is making ethylene or ethene compound. So now let's identify again each one of them as a review. This pi bond, the top one, to make a double bond, the double bond is made of one sigma and one pi bond, a double bond. The pi bond is made from the interaction of unhybridized p orbital on this carbon and p orbital on the other one. So that makes a pi bond. But the sigma bond between this carbon to that carbon is made through a sigma type interaction, sp2 sp2. Always remember, hybrid orbitals, they always make only sigma bonds. Unhybridized p orbitals always make pi bond. So pi bond is the interaction between two p orbitals, a pi bond. A sigma bond is always made of the interaction between two hybrid orbitals or unhybridized 1s orbital of hydrogen with any hybrid orbitals like sp2. So this is an ethene molecule where you have a sigma bond. How many sigma bonds? We have 1, 2, 3, 4, 5 sigma bonds. Ethene is formed from 5 sigmas and 1 pi bond. So I want you to review this at home. An ethene or alkene is made of 1 pi bond from the interaction between pp on each carbon, that makes a pi bond, and 5 sigma bonds. Sigma is this bond, sigma, all of these are sigma, 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 and this one is also sigma. There are 5 sigma bonds and 1 pi bond. I want you to review this. In the next section, I'll show you an sp hybridization and demonstrate with an organic compound to show you how an sp hybrid orbitals are combined to make a compound, a stable compound. And the geometry, as I said, sp2 is 120 degrees. This is important for you to remember. The sp2 has a 120 degrees orientation because of the best overlap for the sp3s. But the p bond or the pi bond, the p orbital is perpendicular to the surface of the sp2 hybrid orbitals. So if you just look at this, if this is a molecule containing the carbon, like flat like this, the pi orbitals are made from this overlap, from standing out, the p orbital standing up like this, making that interaction. That is a pi bond in sp2. So in sp3 hybridization, there is no pi bond. In sp2 hybridization, since there is one left unhybridized p orbital, the unhybridized p orbital makes a pi bond. So I will proceed to the next section, which discusses sp hybrid orbitals. Okay, now we'll be discussing sp hybridization. The same format, the electronic configuration of carbon before hybridization is 1s2, 2s2, 2p2. But now when we say sp hybridization, we meant that one of the s orbital is hybridized with one of the p orbitals. That means 2 p unhybridized orbitals would remain without being hybridized. So let's do the hybridization. The hybridization would give you two degenerate orbitals of sp hybridized. That means one of the s and one of the p would hybridize, and they will contain one electron each. But remember, unhybridized orbitals, which are the remaining p orbitals remain at high energy. Now, if we were to draw this on a carbon, the actual p orbitals. So as I said, the bonding pair, usually where the hybrid orbitals are, usually they want to configure as far apart as possible. Therefore, if you have two groups, the two sp hybrid orbitals. There are two sp hybrid orbitals, and they will be configured as this, so that the bond angle between the two would be as far as possible, which is 180 degrees, which is always known for sp hybrid orbitals. So if I had another carbon, for example, to make a bond, this would have also another sp with one electron, then they are making a bond, and here there is another sp with one pair. Now let's satisfy this by making a bonding with hydrogen, for example. Hydrogen has one s with one to make a bonding situation like this. That is a sigma bond. Remember, always a hybrid orbital with any orbital makes an overlap, which is a sigma type bonding. Here also, if we were to bring on one hydrogen, we have one s with one electron that is being shared to make a bond. So this is how the sp configuration looks like. But remember, you have two anhybrid orbitals in each one of them. So let's say if you have this is the sp orbital of which is containing carbon, there are p orbitals on both, and there is another p orbital in the z direction. So I will just draw the remaining p orbitals, the unhybridized p orbitals on this. So one of them is 90 degrees to the other. So you would have this p orbital containing one electron, and the other p orbital similarly would have, they are equal size, but I'll just draw it here with one electron. So this is, each one of them have, so they would have four of them. So now the other p orbital is 90 degrees to the other one. Therefore, I will just draw this. So it's 90 degrees to this p orbital with one electron here, and this is the p orbital. This is the same p orbital. So this p orbital and that p orbital are 90 degrees to one another. So this one also has a p orbital. So they look like this. So these two p orbitals are the unhybridized p orbitals. Now, remember, all hybrid orbitals make a sigma bond. So this is a sigma bond. Here we have hydrogen, which is already made a bond. This is hydrogen, obviously. Now, when you make a bond, the unhybridized p orbitals make always a pi bond. So this and that would pair up their electrons, they make a pi bond. This is a sigma bond. This is a pi bond. Still now, furthermore, the other 90 degree oriented p orbitals also make a pi bond, because it's a p p overlap. So this actually, when it's representing a molecule like this, so it's acetylene with sp hybridization. So it looks like this. So if we were to account, we have 2 pi bonds, right? 2 pi bonds, because this pp interaction gives you 1 pi bond. This p interacted with another p gives you the second pi bond. And the sigma bond, which is the hybrid sigma bond here, hybrid sigma bond. And this is another sigma bond. This is another sigma bond. So this molecule, the acetylene, would have 3 sigma bonds and 2 pi bonds. So this is how sp hybrid orbitals makes up of a triple bond. So sp2 makes a pi bond, which is a double bond. sp also make a 2 pi bonds and 1 sigma bond to make a triple bond. So now sp3 always makes all sigma bonds. sp2 makes 1 pi bond and 1 sigma bond, that means a double bond. sp hybridized orbitals can make 2 pi bonds and 1 sigma bond, that is a triple bond. Now, so far we have studied a single bond, a double bond, and a triple bond, and they are made through hybrid orbitals. Next, we see properties of some of the triple bonds, this double bond, and also a single bond in terms of bond length and bond angle. So examples of those molecules we have seen so far in terms of hybridization. This is a concept where the orbital hybridization. So as a summary, hybridization is mixing of atomic orbitals. It determines the shape and geometry and optimizes for an overlap. It always makes sigma bonds. The unhybridized p atomic orbitals always make a pi bond. And the hybrid orbitals are all energetically degenerate. So next week we'll come back with another topics in organic chemistry. And thank you for listening.